Okay, what I'm going to be talking about is making learning computer science fun. So I'm a professor of computer science at Queen Mary. I'm also an author, so I'll put the book, 50 Magic Tricks, all teaching computer science lessons. What I've spent my career doing is trying to make computing fun one way or another. I haven't got long here, so I'm not going to do an awful lot of fun activities, but I'm here all day on the stall doing magic, so if you want to come and talk to me and see some magic trick or just be entertained, come and see me on the stall. But I'm also going to talk a little bit in the time that I've got at the end about how to make it effective. I'm also going to need some volunteers, and whoever were the last people in, which certainly are some of the people standing down the side, I need 6 late volunteers. So the last 6 people, could you come up onto the stage while I just talk, please? So it's definitely a few people there. Somebody, you were a bit late, weren't you? Definitely spotted you. But any 6 people will do. 1, 2, 3. Oh, you're safe. Thank you. So, now I've got to make the technology. I'm a Luddite computer scientist, by the way. Technology never works. So it is. So, how do you make computer science fun? The best way of making computer science fun is just be absolutely passionate about it. The more you are just bouncing up around with enthusiasm about the things you're talking about, the more fun it actually is. But also, another way is doing unplugged computing. And there are lots of different things we can mean by unplugged. So it can be as simple as just meaning using analogies and metaphors and things like that. But the more fun ways are when you start doing things like role-playing, you tell stories, you do games, puzzles, magic, mystery. And the point about this, why does this work, and part of why it's effective, is because it makes intangible things tangible. Suddenly people can point at things and ask questions in the world of the physical things that you're manipulating, rather than just something inside of a white box that you've no idea what it is. So it's making things tangible, physical, that are actually abstract, intangible ideas. So I'm going to do one role-playing example. I was asked if I could do something that was really, really fun to start. So this is what I think is the most fun thing I've done. But I am going to talk about how you then make it effective. And this is actually something from 20 years ago from a workshop in Glasgow. So Quentin Cooks used to run something called CS Inside. And he was running a workshop there, and he asked me to come up to do this kind of talk there. And while the teachers that were there were doing a workshop creating unplugged activities, we tried to create one. And this is a variation of what came out of the group of people who were supposed to be running the workshop were doing in the downtime. And it's based on this robot, which is actually what a final year undergraduate student at Queen Mary made. You can go and watch the video. I'm not going to play it now, but it's on Teaching London Computing if you want to see it. It's basically an emotional robot made out of Lego, run with a neural net brain inside it, essentially. So 20 years ago, we had students kind of playing around with neural networks, and we've been teaching artificial intelligence all the way down to primary school for the last 20 years, basically, using things like this. So it's basically a robot that reacts to emotions and shows emotions, essentially. But the trouble with making things like that out of Lego, certainly if you me, is they never work. And also it takes a lot of time, and it's quite expensive. So if Lego are going to kind of give you lots of Lego to do it, then maybe that's fine. But I can't do that because I have no budget whatsoever. And also I watched lots of Blue Peter when I was a kid, and so I like sticky back plastic, basically. So what do you do if you're going to do this? You don't make it out of Lego, you make it out of volunteers and whatever else you've got to have. What is the lesson here? Well, there are lots of lessons. I'm just going to pick one out to use as an example. Suppose what you're trying to do is teach the idea of algorithmic thinking. What is that about? Essentially, it's about thinking of things in terms of computation. So if you're trying to understand something, then if you can model it, if you can write algorithms that do it, and then copy, when you test them, they actually have the same effect as the real world. That tells you understand something a little bit more about the thing that you're modeling. You're turning basically the real world into things in the virtual world and then essentially simulating. That's basically how science is now done, or an awful lot of science is done in that kind of way. So we're going to use algorithmic thinking to understand emotions. So how would you do that? Well, you start on basically programming it, you turn it into algorithms, and this is where I need my volunteers. So rather than Lego, what I've got is sticky back plastic and tubes and all sorts of other stuff. And what I need is two tools. And you're all bound, so like you two will do. If you come and stand here, you're going to be my eyebrows. I'm basically building a robot far faster than I can possibly do this in Lego. Next two tools, people. So hold those up a bit higher, you stand in front, you're going to be eyes, so you get to be an eye and you get to be an eye. And there are two versions of eyes, so you put one of these behind your back and keep the other in front, or yeah, whatever, all behind, but you'll find that doesn't work when you swap to the small one. So behind your back, attention to detail is an important lesson to teach kids about computer science. It really matters. Anyway, and then we need some people to be the mouth. So if you could kind of kneel on either side possibly, and then hold one end of the mouth. So I've just built a robot, and that was a lot easier. It almost went wrong possibly, but it seems to be okay. And this is the other thing about Unplugged. You can do Unplugged as workshops, or you can do Unplugged just as demonstrations in this kind of sort of lecture mode. I do it with undergraduates to halls full of 500 kids at a time, or students at a time. So I only really can do lecture mode stuff. I'm not given the time to do anything else, but it can still be effective that way. But of course, my robot isn't actually doing anything. It's just a model that doesn't do anything. How do we bring it to life? How do we make it do stuff? How do we start exploring emotions? We have to start programming it. So what I'm going to do is program, and so I'm going to do this using decomposition. I'm going to write separate programs for each feature. So I've got an eyebrow program, which I think is the one up there. So here you are, there's I don't know my left or my right actually, but there's one or the other. Yeah, this is the problem with the right and left. It just makes no sense whatsoever. So, anyway, it turns out my instructions are going to be the same for what I'm programming here, so I don't have to worry too much about it. So they've got instructions that are things like if you hear a nice sound, then down. So that just means hold it kind of low. A nasty sound down, but a sudden sound, you push it up as high as your arm can reach. Okay? Now we've got instructions, another program for eyes. This is where you need lots of hands. So memorize it, load it into your memory, and then put it on the floor. And you get. What I'm doing here is I'm uploading my programs, but just putting the program into the computer doesn't make anything happen, of course. You've got to hit run at some point before anything happens, so we can think about different steps of programs being executed. And then we've got the mouth, and this is where things do go wrong. So, we've got instructions like if the mouth's nice sound, then up. What I mean by up is your side goes up. Down means your side goes down, and open means you've got it, you're open. So, I've started whatever position you like, and then we've got to set it going. But what we need is input, and all of you volunteered. What you volunteered to do is make the sound, because basically this robot reacts to sounds, and if it hears nasty sounds, then it reacts to that. If it hears nice sounds, it also reacts to sudden sounds as well. So you've got to make those sounds. So what we need is a nice sound. My robot is born today, so it's its 0th birthday, so you're going to sing happy birthday to it when I want a nice sound, all together. When we have, the kids like this the best, nasty sound, you just make up the nastiest sound you can think of, and make it as loud as you can. And then a sudden sound, I would say 1, 2, 3, and you all shout boom. Okay? So, you got your instructions and the input we're going to test this with. So, let's try this and test it. So, what shall we start with? Well, it's the fun thing, so let's start with a nasty sound. So, on a count of 3, I want the nastiest sound you can think of, and I'll switch you on, you follow your program each. So I've decomposed them, they've all got separate programs, hopefully they're going to work in parallel, and it will all synchronize, but we'll see. So, on the count of 3, you're going to do a nasty sound. So, 1, 2, 3. And does that look like an unhappy robot? Okay, let's cheer it up on a count of 3. Cheer it up, sing happy birthday. So, 1, 2, 3. Okay, that's enough. Okay, and then, what have we got left? Sudden sound on a count of 3. Well, for better effect, let's do the nasty sound, because that's the fun one as well. So do the nasty sound again. 1, 2, 3. Okay, and then let's surprise it on the count of 3. Let's say boo. 1, 2, 3. And it's surprise. And that's basically what that robot does. And what it's doing is it's detecting the tone of people's voices rather than what they say. But essentially, it's the same thing. It's running from a neural network. I'm running 6 different neural networks here. But what we've done here is modeled not actually emotions. There's a difference clearly between emotions and expressions. All we've modeled is expressions. But you recognize the emotions potentially. You know, is this oh, it's not anymore. Is this a surprised robot? So you could recognize the difference. And if you've kind of got, or if I've got the instructions right, you should recognize the expression and also recognize the emotion. And actually, that robot was trained. The student that did it spent hours training it, basically talking softly to it and shouting at it, and basically it learned over an afternoon how to behave. So he trained it like a dog, essentially. And he said by the end, it was kind of quite spooky when he had to take it apart, because it felt like there was something in there, because that's what we anthropomorphize machines, and we really shouldn't. But it's so simple for us to start putting emotions on the back of things and putting consciousness into things where there is no consciousness. As here, there is absolutely no consciousness here whatsoever. In my robot. So, anyway, give them a round of applause. So I'll just make a nice bowl. This is the thing about unplugged. I leave bits of brain splattered all over the classroom, made out of sticky back plastic. I will now try and this stuff. So, there's all sorts of lessons you can do with that. I've used this as a simple primary school first introduction to programs. One is a program, and then we've done that exercise, and then we've got the kids in groups of 6 thinking up extra rules. So they've got to think of some more expressions and emotions, and then try and work out what that means the rules should be that they have to add, what you add to a robot. So you can have evil, winking. We've had people doing the best one I ever had. So this is good for creativity as well. The best one we ever had, one team had an extra 7th person, but one of their 7 people actually had a red jumper. So they set up their robot, and the red jumper kid was kneeling at the back, and we're kind of wondering what on earth is he doing there. And then they had this sort of sound that they said was then sticking the tongue out, and when that sound happened, the mouth opened and the kid dived down. And, is this fun? Yes, it's fun, but it's also learning the basics of programming. There's lots of computational things. I picked out an explanation of algorithmic thinking, but there was decomposition going on there. I did object-based decomposition. You could decompose in a different way. I could have one program that all of them had essentially that was each separate expression. There's also evaluation that we then doing. If you're doing it in that workshop, the kids have to sort of test. They start making faces to each other first, and then they make the robot and the rules, and they test the rules, and we're testing them on you, not just for correctness, but also the sort of user experience. Oh, there's something gone wrong with this slide. So an abstraction at the bottom. Notice I had to explain to you what I meant by a happy set. I've abstracted from the details of what it was, and I just say make a happy set. but behind that, I've given you instructions of what I meant by a happy sound. So that's abstraction. I had to do that with what I meant by up and down. I just abstracted into the words up and down, but that isn't actually precise enough to work. You've got to go into the detail. And that's basically what abstraction in programming, functional abstraction is. Something else I would make the point that unplugged isn't just kind of a way of illustrating things and demonstrating things. You can make it part of the process. So an important, really, really important part of the process of programming that people tend not to do is design. So talk to Jane about this. So her thesis is all about the importance of design, and this kind of unplugged you can use as a design step. So let's not treat it as this is what it was all about. This is just as prototyping. You know, real designers do prototype, and do it with physical things. We're using a physical prototype to get the rules right, and then we're going to program them in Scratch maybe as the next step, which is quite easy to do actually, if you set it up. Or, you know, a step further, we're prototyping it like that before we start building out of Lego and needing expensive Lego and things that are going to go wrong just because the wires aren't connected properly. So it's a way of teaching design, you know, what we mean by design and making it happen. Now, how do you make this stuff effective? I could do that activity in all sorts of different ways. And actually, I did a rushed version in there, so I only barely did what I'm now going to talk about. But what makes this kind of activity effective is something called a semantic wave structure. So this is my area of research now that I'm doing a lot with Jane and Cole Matten. And this is actually based on a sociology theory of knowledge practice. So it's sociology, best subject ever, actually. I'm stopping being a computer scientist. I'm trying to be a sociologist at the moment. What makes a good learning experience is basically you do unpacking and repacking. So you're trying to explain things that are abstract concepts, technical language, jargon. That's what you want people to have mastery of. Mastery of the concepts, mastery of the language, mastery of the practice. That's all the difficult stuff. That's all very abstract, hidden. It's hard to understand. Good explanations link that down with examples, diagrams, metaphors, similes, unplugged activities, to concrete things, to everyday language, to simpler practice. But a good explanation doesn't stop there. You don't just link down. After you've linked down, you link back up again. You repack those everyday things back to the technical things you really want people to understand. So what you don't do, this is stereotypical university, maths at Cambridge, my whole first year was like this. You don't flatline people with just technical language staying abstract. That's not a good explanation, which is why I learned no maths in the whole year at Cambridge when I was there 40 years ago. What you do is you link down. You also don't just do things, oh, it's all a recipe and you talk about recipes, or we just talk about building robots out of sticky back plastic and tubes and things. Because then they just end up thinking, why were you teaching me about cooking? And also what you don't do is link down and stay down, a down escalator sort of structure. Again, they end up thinking you were talking about cooking. First year I lectured, I got feedback that I now understand that's what I did to them. I didn't understand at the moment. But if you link them back up, link back, repack into the things that you're really interested in them understanding, that's how you get a good explanation. And when I came across this theory, it's Cole Matten's theory, I basically went, wow, that explains the things I'm trying to do. That explains why I get feedback, oh, you're good at explanation from university students and so on. It's because I wasn't necessarily doing it well, I was trying to do it. But when I started thinking about it this way, I started saying, oh, I can tweak the things I'm doing very slightly, I can do better. And so this theory gives me a way of actually very quickly and simply thinking about my activities and lectures and written explanations and everything, and just tweaking things, and I can make them better. And the thing to get across, so this is just there's lots more I could say about this, but what you're not necessarily looking for is just this idea of a smooth wave. Real lessons, so this is me plotting a real activity. And what they tend to be is very up and down. It's the unpacking followed by repacking. So here, we've actually got waves within a bigger wave. It's not just one smooth wave, and some of the waves are kind of up and down. If I was doing this activity, to some extent I was doing it a little bit. I start talking about what an eyebrow is, and I'd start explaining the actual instructions. And I'm pointing to code while talking about the everyday thing of what's going to happen. And each of those is doing a very quick up and down wave within the middle of the bigger wave that I'm trying to do. So, exercise for you. Did I actually manage to follow a wave in that overall activity? Maybe, maybe not. Partly because I was rushing it. So Jane and I have been working on, how can you use this idea of semantic waves well. So what you do is you just take a lesson plan, a series of slides, and just take the steps and just ask, is it getting simpler or is it getting harder at this point? Is a simple way of doing it. You can go more technical than that. Am I using more everyday language? Am I using more technical language? And just draw downs and ups and get some sort of profile like this. And then you can ask questions about the profile. So the big one is, does it follow a rough wave shape? At the end, are there waves within waves? How far up and down do you go? Can you go further down? One thing I found is I actually quite often stop early. When I'm going back up, I repack, but I don't go all the way back to the actual definition I started with as my learning active. You will understand this definition or whatever. So it helped me there. Who is doing the packing and unpacking? Jane actually pointed this out, that this ought to be something, because I do all the unpacking and repacking when I'm left to it. I like lecturing, I like talking, I like the sound of my own voice once you put me on a stage. So I do it all. Are you following me? Are you actually unpacking and repacking? It's the audience, it's the students that need to do it. So you reflect on that. Is it connecting to things that they understand? If I'm linking down to recipes and they have never followed a recipe in their life, then maybe it's all meaningless to them. So maybe I've got to do some kind of demonstration that actually shows them the thing that I'm linking to first. And does it concern the actual aims of the lesson? I do magic shows, and I realised when I started thinking about this, actually sometimes what I'm unpacking and repacking is the magic, not the computer science. And I'm really good at teaching magic, but not so good at teaching computer science, and if that's what I'm doing. So these are just reflective questions that you can draw a profile or just think about the profile of what your lesson is doing, and it gives you not right answers, it just gives you things to think about, that if you tweak things, maybe you can make things better and more effective. So the summary of all of this is unplugged computing in all its different ways is just naturally fun. It's also naturally memorable. What you can do, my son said to this, he's busy revising for GCSEs, and he kind of said to me, I know what revision is. It's making things memorable, isn't it? I've got to do things that will make it memorable. Well, unplugged makes it memorable. I still get people coming up to me, years later and say, oh, I still remember the cat in the hat, which is my way of teaching recursion, or one of the ways. I act out the story of the cat. The cat in the hat comes back, I think it is, which is Dr. Seuss book. It's a brilliant description of recursion, used to teach people their first 100 words. Recursion is kind of the difficult thing. First 100 words is easy. Use one to teach the other. Anyway, so we've stuck a name on this, doing semantic profiling with reflective questions. We tend to call this just generally semantic waves. A semantic wave is just when you do have a wave. It's really semantic profiling you're doing. I regularly now do this. I apply this, whether I'm drawing things or I'm just thinking through it in my head. I'm thinking through this, and it's given me clear ways to improve my activities and lessons. Last thing is a favour. If you have heard us talk about me, Jay, or you've come across this through the NCC or CAS or other ways, if you've come across semantic waves and found them useful, we're doing an impact survey at the moment because I've got to try and justify my existence. So the more people who have used semantic waves and can give us some feedback of how or whether, if at all, it was useful, then do so. So if you go back into your classrooms and tomorrow have a go at thinking about a lesson in these terms, have a go, and then fill out the survey, that would be great. But I've run out of time, so thank you. Follow me on LinkedIn and you'll see everything that I publish is free and I'm teaching on computing, so everything's there to download. So thank you very much.